Hello and welcome everyone to the presentation of our paper TAMPAR, Visual Tampering Detection for Parcel Logistics and Postal Supply Chains. This is joint work by myself, Alexander Naumann, and my colleagues Felix, Hertlein, Dörr, and Furmans. Our paper ID is 1322 and you can find the preprint, full code, and dataset for the paper on our project website using the QR code on the left. E-commerce volumes are increasing and thus the amount of parcels carrying valuable goods within the supply chain. When we order something online, the process might look as follows. First, the goods are packaged. Then they are transported to a warehouse, and after the warehouse, the last mile delivery to the client follows. It can happen that the parcel arrives with issues at the final destination. One major issue that might occur is tampering. In this work, we focus on detecting such tampering and thus we want to introduce what we mean by that visually. Here is an image of a parcel and another image of the same parcel after tampering. We consider three main types of tampering within this work. The first one is applying new labels, which is highlighted in red here. The second one is writing onto the label, highlighted in blue. Finally, we highlight an example for adding new tape in yellow. Now, to detect such signs of tampering, we assume that we have a controlled environment within the warehouses, where multi-camera setups are feasible. During the last mile delivery, only cell phone cameras are available. The goal is then to use this visual information to automatically flag suspicious parcels for manual revision. This corresponds to the computer vision task of appearance change detection, which we tackle on a per parcel site surface basis within this work. This task is challenging due to the strong variation in viewing angles and lighting conditions. Before diving into details, we want to outline our tampering detection pipeline. As mentioned before, we assume a controlled environment within warehouses from which we can obtain the full normalized parcel texture. We will talk about what we mean by normalized shortly. Then, during last mile delivery, a photo is taken with a cell phone camera. Our proposed tampering detection pipeline then looks as follows. First, we need to re-identify the parcel on the cell phone camera image to get the above image pair. While Clausen et al. Suggest an approach for this, it is done marker-based in our work. Next, we apply Keypoint detection to identify the 8 parcel corner points. Using the parcel corner points, we can apply a perspective transformation to create 400 by 400 pixel viewpoint invariant parcel site surface views. This is done for all 3 visible parcel site surfaces. Note that these representations are already uniformly rotated with respect to the Aruku marker. Next, we perform parcel site surface matching to identify corresponding site surface pairs. For one such pair, we then apply the final step. We take the site surface representations and apply change detection approaches to classify whether a parcel has been tampered with or not. Before diving into the details of our pipeline, we want to briefly introduce our newly collected real-world dataset for tampering detection and classification. During image collection, we make sure that the parcel identifier and 3 parcel site surfaces are always visible. We collected and annotated more than 900 real-world images, which corresponds to more than 2,700 visible parcel site surfaces. Of these parcel site surfaces, 60% have been tampered with. And as previously mentioned, we consider 3 main types of tampering: applying labels, tape, and writing, both in an easy and an hard-to-detect variant. Additionally, we introduced 6 dataset variants that were created by applying artificial distortions, as visualized in the bottom right. These distorted dataset versions help to assess the generalization capabilities of our pipeline across different cameras. Let's now look at the details for Keypoint detection. We introduced a suitable Keypoint ordering that works well with standard Keypoint detectors. For our experiments, we use a mask RCNN with a ResNet 50 feature permanent network backbone that was pre-trained on Microsoft Cocoa and fine-tuned it on synthetic data from our previous work, Parcel 3D. The results showed that the baseline Keypoint detector already achieves high performance despite the sim-to-real gap. The illustration shows the distortion strength on the x-axis and the average precision for object detection, semantic segmentation, and Keypoint detection. The highlighted area shows the standard deviation across 5 training iterations. The key takeaway here is that Keypoint detection performance is always above 95% and thus mostly robust against the considered distortions. Additionally, we show two qualitative samples on real-world data. Even in this more difficult scenario with damaged parcels, results look promising. Now, using results from the prior keypoint detection step, we can generate viewpoint invariant parcel site surface representations that serve as an input for our appearance change detection pipeline. First, we apply image homogenization approaches to both the reference and the considered parcel texture. 6 different approaches are considered, and the visualization shows a deep learning-based edge detection. Next, we compute the pair's image similarity using a set of common metrics. The results serve as an input for a decision tree of depth 1, which performs the final classification. Thus, the decision tree selects the best homogenization approach in combination with a suitable image similarity metric, and the classification decision is taken by simple thresholding. The best approach combines SimSec, a deep learning-based change detection approach, with LPIPs. Now we take a look at the quantitative performance of the suggested approach. Note that we're only quickly going through some of the main findings and refer to the paper and the poster session for details. Combining SimSec and LPIPs yields an accuracy of 81% and a F1 score of 0.83. The second value for each entry specifies the performance using ground truth key points, and we observe no improvements in performance for this case, presumably thanks to the previously seen high accuracy of key point detection. We additionally performed 3 different sensitivity analyses. The first one shows that the full tampering detection pipeline is robust against the considered distortion strengths. With respect to tampering types, we found that labels are easiest to detect. And finally, analyzing the dependence on the viewing angles also suggests robustness in this case. Thanks for listening to our presentation. The paper, code, and dataset are available from our project website, which you can reach using the QR code on the right. Feel free to reach out via email and directly in the poster session in case you have any questions or are interested in collaborating on joint research. Hope to see you in Hawaii.